This video will focus on looking at the key groups in the periodic table as well as talking about their properties. So when you look at the periodic table, we can kind of break it down into different sections. Based on periodic law, the fact that characteristics are reoccurring periodically in columns. So column 1 is generally referred to as the alkaline metals. They have characteristics in common. And then the second column is the alkaline earth metals. The middle, it's not so much columns as that whole entire D group has similar properties. So we call them the transition metals. And then you've got the halogens, which is that column 17, the noble gases, which is column 18. And then there's other little groups that aren't necessarily columns as much. So you've got the metalloids, got the main group metals, which are those blue ones, and then the bottom two F series with the lanthanide and actinide series. So this video is going to focus on basically the outer edges of the periodic table with the alkali, alkaline, and the halogens and noble gases. So alkali metals come up first. They're in group 1. And again, they were grouped this way based on their reactivity, the fact that they are highly reactive in oxygen. They're super soft metals. They're shiny metallic, but you can like cut them with a knife. They burn just when exposed to air. But now that we've done electron configuration, we can actually explain why they have similarities in properties. So all the alkali metals actually only have one electron in what's called their outer energy level or their valence energy level, which is the electrons that happen after the nearest noble gas. So they all have that S1 electron, and the movement of the S1 electron is what accounts for all the reactivity. So alkali metals tend to lose that S1 electron to become a positive ion, and that is why they all behave in similar fashions. The one other thing about alkali metals is that in this column we have hydrogen. Hydrogen is not a metal, right? Hydrogen can do things similar to this column, which is why it's in this location, and it has one electron in its S1 orbital, but it is not a metal, so don't forget that. The alkaline earth metals then, the next column, which is in group 2, they are very, very similar to the alkali metals, except they are harder, stronger, and more dense. So as a metal group, you can't cut these guys with a butter knife. They have higher melting points in general than the alkali metals. And they react the same as the alkali metals. So they still react in water. They still react with air. But we find they act less vigorously with those things. And now we understand why. When we look at their electron configuration, they have a full s orbital. So while they tend to lose both of those electrons when they're reacting in order to become like noble gases, there's a degree of stability having a full s orbital that makes these just a little bit less reactive than the alkali metals. So the alkali metals lose that one electron, but these guys, they lose the two, but that full orbital has a degree of stability that the alkali metals don't have. Now we're going to jump across the table to our first non-metal group we're going to talk about, which are the halogens. They're in group 17. The word halogen actually means salt former. So if you look at salts that exist, sodium chloride as an example, or salts that we salt our roads with, magnesium chloride, or salts that are in like sand salts or just anywhere that we found salts in the world, we found that halogens were one of the two elements within that salt. So this group became known as salt former. And a lot of times it's these guys with the alkali metals. That's how we form salts. Sometimes you can find them with the alkaline earth metals instead, but those are the majority of salts. Are these guys with alkali or these guys with alkaline? Okay. So they're a non-metal group. They're the most reactive non-metal group, and that's why they group together. They're super reactive because they actually have 7 electrons in their valence shell, we say. So the valence shell is only the S's and the P's. They have 2 S's and 5 P's. So they're just 1 electron away from having that isoelectric with the noble gases, having the exact same. The D block, we find it doesn't matter whether it has a D block or doesn't have a D block, they tend to react the same way for this group. So with just 1 electron away from being complete, these elements tend to gain that electron when they react, which is why they tend to react with like those alkali metals, because the alkali metals want to like give up one, the halogens want to take on one, so it's kind of like a perfect relationship. A lot of these are gases, but they do vary, and they do come as diatomics also. So your noble gases are that last column on the table. When we originally discovered them, so number one, they were hard to find because they were non-reactive. So they weren't a group that you could find bonded to anything. And when they were first discovered, they were thought to be completely unreactive. We've been able to react like krypton and xenon, kind of these bottom ones, we've been able to get them to form actual chemical bonds, but like helium and neon tend to come simply as atoms and not bonded as compounds at all. Okay. Why are they so stable and noble? Well, they have a full S2P6, so all of their valence shell is full. They don't have any room to lose or take on, so they're just satisfied. They don't need anything else. There's lots of practical uses for noble gases, so obviously practical, like filling balloons with helium, but because of their non-reactivity, sometimes when you're doing like welding or other things where fire's being produced, rather than doing it in an environment where there's oxygen, which helps the combustion reaction, we do it in an environment of like argon or krypton, and so then that just dampens the effect of any kind of flammability. So those are your main groups that you have to be aware of. Have a nice night.